related to voltage collapse, nothing but stability aspect of a power system. We all very clearly know stability of a power system is an important expectation and feature related to operation of the system is considered. So power system is an interconnection of various mixed generations to meet variety of loads and typical situations like contingencies, faults, disasters, and any critical issues arising on the operational aspects has to be such that they have to overcome and able to manage the system in stable mode. In that perspective, voltage stability is one important feature one would focus. It is a system's ability to retain the terminal voltage, whatever is specified within the range prescribed, even in the normal mode of operation of the power system, as well as during the disturbances as well. It may be a short duration or it may be a sustained duration, like a transient which will hit and disappear, or a sustained over a period of time. During any such situations, so system must be able to cope up and remain in practice. System may not retain its entire connected loads. Minor part of the loads may be eliminated under the process of balancing or controlling the requirement. Whatever is that, to evaluate healthiness, to understand the response of the system on such typical situation is studied by plot of PV and QV curves. PV curve is a plot of active power drawn from the system at various power factors, and how is that voltage keep changing or impact of that active power draw on the system voltage, whether the system is able to provide required active power demand at any cost of voltage, or when is that certain voltage and below voltage falls, do system will be there for your operation or not, is understood by PV curves. So therefore, PV curve is a plot of active power and voltage of a system. Similarly, QV curve, reactive power and voltage of a system, which these two parameters help to understand how is that voltage falls seriously. Rapid fall of voltage can be studied, or when is that rapid fall of voltage occur on the system whenever a demand rise in a rapid manner. So if such situation is likely to occur, then you can protect that occurrences. So that is how voltage collapse is a serious fall of voltage due to the demand. So that if you are not protecting, voltage collapse will continue and entire system will suffer fall of voltage, and all the equipments interconnected which are sensitive to the voltage start malfunctioning, start acting wrongly. That cause a major disaster in the system. In that perspective, PV and QV curves are referred to study stability aspect of a power system. That is the scope what we are likely to see. What is PV curve, what is QV curve, how that will help to assess voltage stability of a system. Let us see these curves. PV and QV curve. You can see one of the curve I have taken from the one of the presentation, plot of voltage and power. You can see in this diagram, as the power demand on the bus keep gradually increasing. You can see from the 0, P0 and PM maximum what it can give. This is the margin where it can permit the sudden change or whatever the change in demand. But see the voltage that's scheduled per unit, which is able to maintain the voltage even from 0 to certain scheduled voltage and a maximum what is permissible. The voltage start decreasing gradually like this way. You can see when we have a loading effect on the particular bus, definitely active power demand will cause the deceleration of the generating systems. That deceleration of the shaft of the turbine definitely make the terminal voltages to collapse, so that excitation system need to work there. In that purview, when the loading effect occur on the particular power system bus, voltage is sure to gradually fall in nature. There would be again a limit of voltage. What is that drop in voltage permitted? Can I accept whatever the voltage drop is noticed on the system? Let it be there. Let it keep on delivering the active power, whatever the demand comes on the system. That is not a technical acceptance. So there should be a limit mentioned, plus or minus tolerances for V. Beyond that variation, system loses the stability. Therefore, that is viewed once again in the next neighbor diagram. We can see the plot of voltage again with the P. The plot is showing you like that. As the load of the power system keep on increasing on x-axis, you will find the drop of voltage gradually noticed. Further, any megawatt excessive loading, voltage starts seriously falling down. Certain point of voltage, you can see V critical. So this is a certain voltage. Any further loading of megawatt on that system will make massive fall of voltage. Voltage start decreasing rapidly. So you can see this comes down. And you will find the P max, what you are trying to load from minimum to maximum, further any load of P max will not contribute P max, because P transfer from a bus to another bus, P12. If I write by equation, it stands as V1 V2 sin delta 12 whole divided by x12. It is a power transfer between any two buses. It's a general equation. There comes, for active power transfer between two buses, voltage magnitudes of the buses 1 and 2 which are involved appear there. Therefore, if there occur an incremental load active power on the system, by the PV and the PV curves of a system, it is noticed that certain megawatt P and later you cannot increase, because certain P increase on that station will cause massive fall of voltage. That's what you can see. This curve show you certain P, as you are increasing on the generating particular bus, there is a follow-up of voltage by falling nature. Certain voltage comes and stand as a critical. Further loading beyond that will not support your voltage. Voltage starts seriously falling down. This we call as voltage fall or a voltage collapse. Further loading is not possible. Then we must understand what is that critical voltage. This is called critical point. So the zone from this nose, the nose of this curve, we can see here critical point. The slope of the curve changes here. Slope of the curve upper half, slope of the curve in the lower half at this critical point, we can say I can regionalize, such as the stable limit is above. The point and above region is stable. The point and below region is unstable. Between this left half, this one, stability limit. It is a stable operation system till a critical point. So therefore, this criticality need to be understood. So this is understood by PV curve. This is for one certain P at a certain power factor. Suppose if I have number of curves drawn of P at certain voltage at a different power factor. If I show you another curve, can you visualize this curve? This curve, this is the plot of V and P itself, but P is per unit. V is per unit. It is called as normalized voltage. We will not worry about this. What is this V equal to? Let us say ordinate is a voltage, abscissa is a power. It is a plot of PV. Then this was the system considered a bus, and there is a load bus. There is a draw of power to the load. So the power factor of the load is changing. Suppose power drawn at tan phi, it is given in a tan of the angle. It is 0.75 minus. How is that load P and V behave themselves? This is like a curve plotting. Certain critical point is noticed here. Further loading is not possible because voltage starts seriously falling back to zero. Suppose tan of the phi of that system. Phi is the power factor angle of the load here. So tan of the phi, if I take, if it is 0, then plot of P with V. As the P changes, this is the profile of the curve. Inner curve from 1 PU normal, it starts diminishing and certain point is attained. This is called as a critical point. Any loading further will cause the voltage collapse like this. This is the another curve at tan phi equal to 0. Similarly, several curves pertaining to the load type at tan phi equal to 1, tan phi equal to 0 and beyond. If I plot, I have series of curves. So each curve possesses a critical point at the nose point. We call it the nose of a curve. So these curve, critical point, another critical point, another critical point, and so called all the critical points, if I join by a line, we call it the locus of critical point, that regionalize upper half as a stable limit, lower half as a unstable limit. So this is the nature. When I have a particular bus delivering a power, for a certain power factor of that, which of the curve is followed by that delivery. So I have to see, suppose it is following a curve number 2 from my left hand side. If this is a followed path, then I know what is that maximum power I can deliver, more than just about 0.4 pu. So I cannot load more than 0.4 because this reflection show that 1 pu voltage definitely going to diminish and follow immediately to 0 when the loading effect occurs. So this is going to help to assess voltage collapse nature of that. Likewise, I have several curves plotted for a system for various power factor angles. So that's what I am speaking. This is one typical curve I have shown you here. One curve at a particular point of criticality, the slope of the curve changes. That bifurcates the location into stable region, unstable region. This is a critical point. Beyond this P max, I cannot load this. If I try to load, definitely voltage start falling down and P also start falling down because P is V1, V2 sine delta 1, 2 divided by X1, 2. That definitely affects V, that in turn affect P. This is how PV curves of a system help to evaluate the stability aspect of the power system. So similarly, if I have a representation of a radial system, this is what I can get into. If I want to know QV curve, plot of reactive power delivered from a bus with respect to voltage. As we know, as per the operational aspect of the power system is considered, active power delivery balance, reactive power delivery balance at specified voltage is very mandate. It's a dynamic phenomena. The system has to work and try to balance these two. In that view, suppose QV curves of a system if we study, it is a plot of reactive power and the voltage. You can see reactive power taken on a ordinate vertical axis because reactive power can be supplied to the load or reactive power can be absorbed by the system itself. In that way, you can see the mark injection and absorption like that. The reactive power is supplied to the system, means loads are absorbing or system is absorbing the reactive power. How is that voltage of the system going to behave in such scenario? Let us take this curve at the right corner at the lower part. It is a plot of V and Q. Again, reactive power limit at a certain point maintaining the PU1 of the voltage. As the reactive power demand on the system increases, you can see here, there is a direct relationship between Q and V. If there is an insufficient delivery of Q to the requirement, voltage start falling down. That's what the notice. When the frequency and the power and reactive power and voltage are connected strongly one to another. As per the variation of reactive power, as you can see the plot here, reactive power demand increases, gradually you will find a dip or diminishing voltage. Again, it follow a particular path. How long this drop is acceptable to the system? System find certain operating stability criteria. Beyond a particular critical point, any fall of voltage is not advisable because the compromise of certain fall would really cause an adverse effect on remaining connected systems which are swinging parallel. So they will suddenly get affected, and this fault or this disturbance protrude into the system, causing an oscillation of all the components simultaneously and create a blackout or such a disaster. In that perspective, the reactive power limit, once it is seen, certain Q max, when the system is absorbing certain drop which is reached to a critical point, further drop, further limit or further increase of absorption reactive power from that system adversely affect the voltage profile to go back. Again, this also regionalize the point of criticality into stable region, unstable region, and stability limit. So system must be operated in this area only, because we have to operate the power system very defensively to see to it that P balance, Q balance is worked out. For the shortfall, we have to take adequate measures, whether to increase the generation or to curtail the load or to adopt compensation. That could be a scientific solution for the current requirement. But as a reflection of the system is considered, QV plot show you for a certain Q demand which is increasing on the system, as the fall of voltage is noticed, a critical point is observed. Any variation of Q beyond that point seriously affect the system voltage, which is not desirable. That is being noticed in this QV curves. So therefore, when we plot the actual ability of the system to transfer reactive power from the bus to the load, or ability of the system to absorb the reactive power whenever loads are suddenly rejected, whether system is inherently capable or not, is put as a graph of the reactive power ability and the voltage profile. It looks like a J-like curve here. It means certain P is worked out, certain megawatt you are delivering. What is that Q limit, Q ability we are checking? This one of the curve show this is having a transfer of reactive power to the system, as well as absorption is also possible. So the curve is covering both the reasons. This curve is a plot of ability of delivery or absorption of reactive power of a system. This is having an injection provision. It is having an ability to provide reactive power, as well there is a drop of sudden loads able to absorb the reactive power also. This is Q margin show you this much of MVAR can be suddenly absorbed by the system itself. So if the curve is touching this x-axis, being away above like this way, you can see that shows system is stable but not having any margin of Q limit absorption. I'll show you some curves over here. You can see this curve, which I can see here. This is also QV curve, the plot of Q and V. So each curve is having a certain power factor, meaning certain power. Active power is fully delivered. P is 1 PU, P is 0.75 PU, P is 0.5 PU. Like that, certain active power is noticed. And to deliver that, what is that reactive power? Along with that, being pumped to the system is plotted as QV curve. You will find few of the curves are above this x-axis and few of the curves are shown below this x-axis, which is nothing but absorption and injection of reactive power if I consider. By this way, having the various plots plotted on a common scale for a system noticed, I will come to know the behavior of the system during certain loading condition, whether a system is having an inherent ability to deliver or absorb reactive power or not. This is going to be an knowledge we get from QV curve. And I was speaking about this, the nose or crest of this point. When I say a particular point, as a loading P megawatt keep on increasing, indirectly Q is getting affected. See here, we are speaking about active power absorption. Along with that active power absorption, load do consume reactive power. That reactive power seriousness is also there on the voltage, and certain point later reactive power, what is flowing or what is being absorbed by the loads, seriously affect the voltage profile of the system, causing voltage collapse. Now I am in a good position to tell you what is voltage collapse. Voltage collapse is a very serious, dangerous phenomena noticed in the power system operation, wherein the serious fall of voltage due to drawal of active and reactive power rise, or rapid drawal of active and reactive power certain critical point, and later it is not possible by the system to cope up with that. What will happen at that critical point? Suddenly massive fall of voltage is observed. Therefore voltage collapse is a very serious phenomena. Certain point and later stability of the system is lost, so voltage comes very drastically lower point. That in turn will affect rest of the connected system, seriously get affected in that way. Therefore, to study that, PV and QV curves are referred. So I am just referring here a real system PV curve. Then I am referring here a QV system, and when is that absorption, when is that delivery takes place. From this we get one important aspect. What is that? Voltage collapse proximity indicator. This is one important definition. Voltage collapse proximity indicator, VCPI. This is defined as dQs by dQr. QS is called sending end reactive power. QR is called receiving end reactive power. It's just a ratio. You can just see in this. So this is an indicator. I read out here where QS is sending end reactive power, QR is receiving end reactive power. The implication of a higher value of VCPI. So value of this, if it is a higher, it indicates that as the load increases, is that large amount of reactive power is needed at the sending end to support small increase of load. So increase in VCPI factor is an indicator of impending voltage collapse. Impending voltage collapse in the sense the very upcoming, prone to, very sensitive and likely to experience voltage collapse. This is the measure. dQs by dQr of a system, if it is measured, that indicates the probable indication or a identification of upcoming voltage collapse phenomena. So this parameter is very important, one should know. So this way PV and QV curves are very important for us to understand. Moving to another heading, let me come. So it's another important aspect, reactive power required for the specific receiving end voltage. So it means to say, I'll not touch upon this. Whenever there is a need of reactive power and certain receiving end voltage to be maintained, what is that sending end voltage profile? We know that in case of a transmission line, sending end voltage, sending end power, sending end current, sending end power factor. Similarly, the other end of a transmission line, receiving end voltage, receiving end power factor, and other aspects connected by transmission line parameters either in impedance or admittance domain. Definitely, receiving end voltage need to be maintained at specified value. To meet that receiving end voltage, sending end voltage profile must be such a way capable higher such that subsequent drops what would occur, subsequent loss what would occur should be taken care, such that at the receiving end that will not be reflected, that will cause maintain specified ratings. In that due respect, what is that reactive power really required to be supplied to the system to maintain receiving end voltage constant? That is the heading here. In that heading, just see the curves here. So receiving end voltage versus distance from the sending end of a transmission line. These various curves, curve A, curve B, curve C, and curve D have a self description. No load, no compensation. Transmission line is a very long line, about 800 kilometers, which is mentioned here. No load, nothing is there as a load, and no compensation. The the profile of the voltage, receiving end voltage, as we go with the long transmission line, definitely it is superior because of the distributed capacitance of the transmission line become leading volt ampere, improves the voltage profile having reactive power available with that. Then second one is B, no load with compensations at both the ends. It means sending end we have a compensating devices, receiving end we have a compensating devices, but load is not drawing any power, as if no load. This is the profile. 1 pu voltage is just about 1 pu, a swing around that. This looks to be a very stable mode of control of receiving end voltage from the sending end perspective. Look, if you look to the C point, no load, there is no load drawn at the receiving end with the compensation at ends and center. So it means to say, now there is a good scope to think. Where do you require a compensation? Whenever there is an absorption of reactive power. Reactive power need to be substituted, compensated at the point of need only, because transmit of reactive power over a long distance cause higher drop and it is non-economical. That is a factor associated with which. Therefore, where do you compensate? That's called as a point of compensation is very important. Generally, whenever you have a long transmission line, sending end, receiving end, and midpoint compensations are referred. That's what the point C says. There is no load at the receiving end. Compensation is at the ends as well as at the center. This will be the profile. The voltage of the receiving end will swing about this and swing. This is the good way of keeping the voltage profile of the system. So this will leave sending end voltage safer or not going to have stress on a sending end. And the last one is natural load with the compensation at the center and ends. There is no such specific load, just a casual load which is called natural load with the characteristic impedance at the load side. This is how voltage falls. You can see. This is just to say the need of reactive power to maintain certain receiving end voltage as specified, which we need to provide from the sending end at the different levels of its length of journey, a compensating devices, such that you are able to view receiving end voltage as expected. That's what is the outcome of this particular heading, reactive power required for specific receiving end voltage in long transmission line. These four curves depict what exactly is needed by this. Okay. And we'll just go to few of the problems. This is what the theory portion under this chapter. We have about 5 to 6 problems. Let us focus which have really appeared in the exam. These are the questions which have really appeared in the exam. These are the textbook examples only. Therefore, it is very easy for you to get to me once and you can refer yourself in the textbooks for your clarity. So I just read out a 11 kV generator supply a load of 100 megawatt at 0.92 lagging. It is connected to a load through 11 bar 132 kV transformer and a transmission line working at 132 kV with the impedance of 20 plus J60 ohm and a step down transformer at the receiving end. It is 11 bar 132. Definitely 11 bar 132, that should be 132 bar 11 as usually we label it. So this is a step down transformer. Both the transformers are equipped with taps. Tap changer is there at both the sides. Then a design criteria TS into TR is equal to 1 maintained. Determine the tap settings if we need to maintain the receiving end voltage at 11 kV. So this is the scenario, one derivation we have done. We have viewed it. The similar diagram is taken over here. Sending end voltage you can see here, which is 11 kV. After the transformer, it is 11 bar 132. And other side, it is 132 volt bus. And receiving end side, you have your receiving end voltage 11. So 11 is sending end, 11 is receiving end. In between, transmission is at 132 kV. So you are transmitting the voltage at 132 kV. and the transmission line impedance Z is mentioned as 20 plus J60. And the transformer at the sending end, transformer at the receiving end have tap ratio or tap changers, which TS and TR are given. And we know by theory it is 1:TS at the sending end and TR:1 at the receiving end. This was the derivation. I go back and tell you where we have seen it. So the derivation we have observed. If you are not viewed it, let's view once. Nothing wrong in that. This was the concept I am trying to highlight. 1:TS, TR:1. This was the mechanism. On this mechanism, these are two equations. You can see here. Equation 1, equation 2. On these only, your calculations are based, which I will be showing you in the problem. Okay. Let's view this. Okay. I have V1, V2, sending end voltage, receiving end voltage. 1:TS, TR:1. P and Q are the loading values at the particular station. So therefore, let us work it out. Let us choose base of 11 because we are sending and receiving end voltages are 11 and 100 MVA is the megawatt. Then 11 kV 100 is the base of the system. Then voltages at the V1, V2 after the transformers primary side and at the receiving end side I have 11 kV, that is referred as 1 pu. So then load of 100 megawatt at 0.92 lagging means this is the load at this side, P1 or PR and QR. So what is the load active power? 100 megawatt. What is the reactive power? I have to convert this. 0.92 is what? Cos phi equal to 0.92. What is the reactive power? If you recall back active and reactive power relationship in a power triangle, the hypotenuse stands as apparent power, adjacent side is the active power, opposite to the angle, vertical side stand as reactive power. I am in need of reactive power with the active power. Active power is 100 here, plus J times reactive power. What is this numerical value? This numerical value is this 0.92. You convert inverse cos. Inverse cos of 0.92 give you an angle. So tan of that angle you operate. You will get 100. Listen to me. 100 tan phi. Tan phi. Phi is the angle obtained by this after cos inverse. Cos inverse 0.92 give you a phi. Tan of that into 100 give you 42.6. So please note this. I am repeating this. Probably you will be in confusion otherwise. Once you know, mostly you will not be confused. This is the reactive power. Or if you know the power triangle concept, hypotenuse is the apparent power, adjacent side is the active power, vertical side is the reactive power. This value which I am speaking, 42.6 is vertical side, 100 is adjacent side. Hypotenuse I have to get from this if I require. It's called complex apparent. So when I take 100 as a base, divide it by 100, it turns out 1. This turns out 0.426 per unit representation. So therefore, be very careful. Problems are very, very simple. But we have to work very carefully on the particular requirement. So given data is processed here. Stepwise, if you do, by this time, 1/3 of the marks you got already by this. Next is base impedance of this hat, because impedance of the line is given. What is the base impedance from this given data? MVA is given and I know the kV also for this particular section. What is the kV working? 132. So base impedance is 1 kV square, 132 square divided by MVA. That stand as 174.24 ohms. So why I am converting this, you might ask me, because my calculation is going on per unit. Then I must know base impedance. When I take that base impedance to the impedance of the transmission section, I can convert the impedance of this section into per unit. That's the reason ZB, base impedance, is required. kV square divided by MVA, 174.24. Then what is the load, this one? Data of your transmission line, 20 plus J60. Can you see here? Line, impedance of the line equal to 20 plus J60. When I divide it by 174.24, what I'm going to get? Actual impedance divided by the base. It give me per unit impedance. You can see 20 by this number goes 0.114 plus j 0.344 pu. I converted impedance of the line into per unit. So I have per unit voltage, per unit loading, per unit impedance. All my calculation go now onwards per unit only. Therefore, using this, I use the equation. Just now I have referred you a quadratic form of equation, V2 square minus Ts square V1 V2 plus in the bracket Rp plus X2 Tr square equal to 0. This was the equation. I go back and once again revise you. What was the equation I am using? This is the equation I am trying to utilize. This equation. Listen to me. This is the equation. This equation I am trying to use. Here resistance, reactance, active power, reactive power, Ts, which is required to me. V1, V2, per unit 1, 1, V2, 1. I am substituting here. So it's a very simple just substitution of this one. You can see. So V2 square, 1 square, Ts as it is, Ts as it is. Remaining all 1, 1, Rp, X cube from this value. Just from this, whatever I got, I'm just placing here. And I'll solve this equation. I'll be getting Ts equal to 1.16. Once I get a Ts, given there is a design criteria, product of Ts into Tr must be 1. With this, what I'll get? Ts, I know. Ts into Tr equal to 1. I just take inverse of this. That is 0.86. So there should be Tr, which should be 86% of the tap. This must be 1.16%. Means it is in calculation. So therefore, this is how you get tap settings at the sending end, tap settings at receiving end. If I work it out in this way, 11 kV what I am pumping over here is able to be or able to get 11 kV at receiving end, keeping the 132 kV line with the help of tap changers. So this is how sending end tap and receiving end tap values are obtained by this example. Very simple example, worth 8 marks. Kindly note, this is a very simple exercise. Similarly, if I go next problem, this you might have seen in EPU, electrical power utilization or the utilization of energy. What is this? This is called, please.
Sir, in the last problem, sir, why should we have to divide ZL by ZB, sir?
Yeah, to get into base units, per unit. This ZL is transmission line impedance, which is of like whatever the value, resistance and reactance. It is in ohm manner. It is given in ohms, correct now? Then the values of voltage at the sending end and receiving end are in per unit, and powers are computed in per unit. Then when I want to use this impedance in this equation, which is V2 square minus Ts square, these values, all the values are per unit. That is the reason I have to convert R and X of the given transmission line into per unit. That is the way impedance base I have to calculate. Actual quantity divided by base quantity give you per unit. Okay? To get into per unit, that is the reason. Because all the values are computed on per unit basis only. That is the only reason. Okay? And this problem is like an UEP problem, which is called load side compensation. Let us read it. You will get into this problem very easily with your electrical power utilization concept. A 440 volt 3-phase distribution feeder has a load of 75 kilowatt drawing a current of 130 ampere. A capacitor rating 45 kVAr is connected across the load. Determine the power factor and reactive load before compensation and PF after compensation. It means you have a 440 volt 3-phase long feeder. Load at the end of the feeder is 75 kilowatt. It is drawing 130 ampere. Okay. Then if you adopt 45 kVAr capacitor to the feeder, what will be the power factor of that? If it is not used, what is that power factor? It is called improvement of power factor of the line. Nothing but reactive power which is being absorbed is compensated by the reactive power applied by the capacitor. This is to correlate that. Let us see before the compensation. We know that power in 3-phase is √3 VLIL cos phi. Yes. Then power factor of this load 75 kilowatt can be calculated as what? 75 kilowatt divided by root 3 V into I, which says before compensation actual power factor is 0.757. So we know that the reactive power absorbed by this without the compensation, without any capacitor addition is Q. Q is P tan phi. How we got it? Again a power triangle. Power triangle, if I draw a right angle triangle, adjacent side becomes active power. Vertical side become reactive power. Hypotenuse become complex power total. Then tan phi is used to connect non-active power with the reactive power. P tan phi refers reactive power. So it is 75 kilowatt into this phi. It is called cos phi. Get cos inverse of this. That's an angle. Tan of that you operate here. Tan of angle into 75 kilowatt give you reactive power. It means to say this radial feeder, distribution feeder is delivering 75 kilowatt power as well as 64.73 kVAr reactive power along with that. So therefore, what is the power factor from this combination? 0.757. This is without any compensation. Suppose if you incorporate a capacitor of 45 kVAr, so what exactly happens here? The reactive power absorbed by the system is 64.73 kVAr. You are artificially providing by a capacitor a capacity of what? 45 kVAr. Then what will happen? Demand on the system definitely become less. 75 kilowatt when it was drawing 64.73 kVAr without compensation. When I apply a compensation, 45 kVAr is provided by the capacitor. Difference of this is the only load on the system. That you can see here. Because of capacitor, reactive power of that is 45 kVAr. Total reactive power demanded is now actual load, which is 64.73 kVAr minus 45 kVAr. What it results me? 19.73. Now you can see without the capacitor, the demand was 64.73 kVAr. After the installation of the capacitor, what was the demand on the system? 19.73. Demand of reactive power is reduced. What it should indicate you? It will indicate improvement in power factor. That's what is we call it as power factor equal to cos of angle I want. Angle is inverse tan reactive power divided by active power. Reactive side divided by active power side. Reactive power side is now compensated side. 64.73 minus 45, that is 19.73. That is divided by 75 P. So Q by P inverse tan, that give a angle. Cos of that power factor. So it makes 0.967. You can see a change here. It was 0.757 without compensation. After capacitor installed, power factor became superior to that. It stand as 0.967. So this is how improvement of power factor by adding a capacitor. Reactive power injection. This problem is called as reactive power injection and maintaining the voltage appropriate. So this way a simple numerical works out. Then here I have similar example. If 415 volt 50 hertz three-phase system deliver 500 kilowatt at 0.8 power factor, shunt capacitors are installed to raise the power factor to 0.92. It was 0.8 in reality. Capacitors are installed to increase to 0.92. Determine the value of capacitor needed. So there is a question which is not completely in this problem. One is if it is star connected. If it is delta connected is our line missing here. So it is the same problem. This was this kind of problem only, describing it such that connection of the load is star, connection is in delta, like that. That you can see. The value of capacitor depends on connections, star or delta. The reactive power supplied by a capacitor bank is, you know, Q equal to active power inside the bracket tan phi 1 minus tan phi 2. Hope you remember that triangle where two triangle one inscribed in the other, the vertical sides are shrunk down and phi 1 phi 2 are the angle included by that vector. Then P tan phi 1 minus tan phi 2 give you the reactive power. So this kind of problem you might have solved in UEP. So therefore, if you utilize 0.8 to 0.9 shift, please mention them. Once I mention tan of the phi 2 with a 500 kilowatt, that capacitor required is 162 kVAr. To shift 0.8 to 0.92, this is the reactive power I must install. Then per phase means divided by root 3 phi 2, it become 54 kVAr. The per phase. Now, suppose the connection is star fashion, then I know that IPH equal to I line in star connection. Then what is that current really flow? With this 500 kilowatt, if I take it, P divided by root 3 VI cos phi concept, power divided by root 3 V into cos phi, which is 869.5 without compensation. Am I right? Without compensation. Power factor originally it was 0.8. Without power factor compensation, it was 0.8. This led me 869.5 ampere. Now from this, we know that when I have a current I cos phi, I sin phi are the two components of that I can divide into. I can get the component of that in a cosine operated and sine in quadrature in line with that. So therefore, I have active component of that as I cos phi, which is 869.5 into 0.8. Give me this much ampere. Since active power remains the same, active component of the current remains the same, the reactive component is given by I sin phi. I was just picking. This is the main current. I cos phi, I sin phi. Active and reactive components of that. I sin phi works this way. So I am substituting this, it become I active current tan phi. So if I use this for a certain capacitor per phase, what is the current actually supplied by the capacitor? I want to calculate that. You can see the active component of the load current without capacitor is IA tan phi. Okay. Then reactive component of the load current with the capacitor is IA tan phi 2. So phi 1 is without compensation, phi 2 is after compensation. Therefore, what is that current drawn by the capacitor? IC. Like what is that reactive power? How we do in terms of current domain? It is IC equal to IA inside the bracket tan phi 1 minus tan phi 2. If I calculate, I'll be getting current drawn by the capacitor, leading current drawn by the capacitor in ampere. This is going to be helpful to me because I square XC is the reactive power component. IC square into XC you become QC. Then from this QC, which is known to me, which I am going to inject or connect, if it's known to me, this with the component IC square into XC, if I equate XC, I can take out. Capacitive reactance of that I can take. Reactive power delivered expected equal to IC square into XC. IC I know. QC I know, only XC I do not know. I can calculate XC as QC by IC square. This XC is what again? 1 by 2 pi FC. Get the C value. C value stand as 2995 microfarad per phase. So this is how per phase QC required, and capacitance per phase is 2995 microfarad. If I would have installed it, it would have ensured me the power factor of this particular system, which is delivering 500 kilowatt at 0.8 PF lagging, would have risen to 0.92. And the shift of 0.8 to 0.92 cost you installation of the capacitor per phase 54 kVAr. Correct? Then capacitance, what you would have used is 2995 microfarad. This is a very simple UEP based problem. Just you have to visit with the reactive power perspective. Similarly, if it is a delta connection, as you know, delta connection, line current and phase current are not the same. Phase current is line current divided by root 3. You can see there 869.5. We got it here as a main current. That divided by root 3 to get your per phase component. Then what is that active component out of that? This current into cos phi. You'll get this one. Correct? Then current drawn by the capacitor is main current, tan phi 1, tan phi 2. This will be different in value. Then what is this Xc equal to? Xc equal to what? Ic square into Xc equal to capacitance, 54 10 to the power 3. This give me Xc. This Xc with 1 by 2 pi Fc, if I calculate, I will get capacitance as 998 microfarad. My friends, by this you have to note very carefully. Whenever you are applying a capacitor-based compensation to the system in 3-phase, the connection of star and delta matter the more. You can see here, capacitance per phase became normally 1000. If I round off it to 1000, what about this? This is nearly 3000, 3000 and 1000. Now you imagine. So whenever you are working on the system, you must be cautious. Capacitors are connected in star fashion for the compensation or delta fashion for the compensation. You shall not disturb it, because disturbing the one, it will affect the other. You can see here 3000 and 1000. There is a tremendous difference. You can see, note that value of capacitor in delta bank is 1/3 of the capacitor bank required in star. Are you sure? This is because per phase voltage and line voltage are one and the same in delta. So therefore, you must be very careful in working with the numerical content. So capacitance is 1000 nearly microfarad because of the nature of connection. So therefore, you shall not misunderstand this. This is really the correct phenomena in 3-phase star and delta. As you are known, the power handling ability of delta is 3 times greater than that of star. In that regard, all these things are technically correct. Similarly, I have one more with the motor perspective. You can just glance this. Power is given, reactive power is computed, power factor is same outline. Q equal to P tan phi 1, tan phi 2 like that. Then this another example which is just shown you, an alternator supplying, very simple problem. Just I outline this. This is really required for you to know how the transmission line reactance is compensated by series capacitor. How would power transfer increase? That is the meaning of that. Impact of that on power angle. This is how a simple problem give you an outline. An alternator is supplying a power of 0.8 pu to an infinite bus. The total reactance of the alternator, transformer and the line is 0.8. All together, it is called from the generator, transmission line and transformer incorporate from end to end. Entire value is 0.8 pu x. If generator terminal voltage is 1.11 and bus voltage is connected to is 1 pu, determine the operating angle of the alternator, delta. What is the maximum power that can be transferred? First thing, if now a series capacitor is added to bring down the total reactance of the line to 50% of the original, find the new operating angle. This is a series capacitor concept of compensation of the transmission and reactance is very strongest phenomena of compensation. So if it is so, how is that is the meaning? We know the very basic equation. Power transfer between any two buses P is bus voltages Eg Eb sin delta divided by X. P is given as a 0.8 pu, Eg Eb mentioned to us, and total path reactance is also mentioned 0.8. And sign of the delta I have to get. Delta equal to inverse sine ratios. That you have to get. So maximum power by this way is what? Eg into Eb divided by X, sin delta goes 1. Then delta is 1, that is the maximum power transfer, 1.375 pu I can get. With the compensation, let's see, the denominator of that equation, P equal to EG EB sin delta divided by X, X is becoming exactly half of the original. You can see that 50% of 0.8 is 0.4. You can just see. And it is retaining same power delivery. So maximum power transfer is 0.8 PU 1.1 into 1 divided by 0.4 into sin delta. What is this delta at that time? The series capacitor is added to retain this power transfer. What is that power angle? For this, my friends, you recall back one of the experiment you have done in power system laboratory, where you have power angle curves, plot of power and delta. As the delta angle keeps 0 to 180, the power transferred from bus to the neighbor keeps rising forward, attains its peak at 90 and start falling down to 0 when it reaches to 180. So this angle is of that nature, correct? That's what the delta we are trying to think about. So this very simple problem, how series compensation makes the things possible. So here you may find, instead of telling you what is the power, what is that angle, the question may be something like this way. What is that power transferred if the transmission line reactance is reduced to 50%? P may be questioned to you, and this X is reduced to certain percent, given you the same initial angle 35.58. Then you may get P computed. When X is reduced, P has to rise actually. With the same delta over here, X is 0.4, you can compute P. P must be more than what it is originally. That is the meaning of series compensation effect. So the question can be twisted in and around that. You will be able to answer it very carefully. So look carefully the question what you understand in a diverse manner. Think and work into. Similarly, I have the transformer based simple substitution problem. Reactive power supplied is given by T into 1 minus T V square. This is one of the equation which I was speaking over here. I go back and come back. This is the equation. This equation, the second equation. Reactive power supplied by the transformer tap changer mechanism is given by this T outside 1 minus T into V square by X complex. Correct? This equation is used here, just a substitution. Kindly go through this, you will be able to get what is the gist of that. Okay, it's very simple, just it is given as a total value in this area I'm speaking. And this is another simple aspect. So you have a transmission line, you have a transformer, two lines. One is underground line, another is the overhead transmission. The history is given here. Upper arm is overhead transmission line, lower arm is representing underground UG cable. Then current drawn by this. So they are asking you the current through this, current through this. This is a complex calculation, just a ratios. Just I'll turn up and see. You can just see, just a complex current division technique. Very simple. Just you can see what is the current here I can get. If the current is here, what is the current that would come here? What is the remaining current here? So how the ratio can be taken? The same thing is given here. You can just see. This is a complex polar rectangular ratio current division technique. Correct? So this is very easy. Once you glance, you will be able to get this. Okay? The same thing. This is little interesting and a problem of your examination like. Consider a single phase line of 220 kV, length of 200 kilometer. The resistance per kilometer is 0.0, unit length and resistance 0.01, 0.031 ohm, and reactance per kilometer is 0.32 ohm. Compute the sending end voltage and accurate and approximate using formulae. If the load is 500 megawatt at a power factor 0.85. So this is obtained. Take you back, which is the concept applicable. Okay, this will be very interesting for you people to note it down, because when you know the concept, solving is not a big issue. I'm here. Dependence of voltage on reactive power. This is the derivation. This is the equation I am trying to use in the problem. So this kind of concept, dependence of voltage on reactive power concept, using this equation, I am trying to solve this problem. Clear? I come back here. So you have been given with a base of, but here base is not mentioned here. In the examination problem, use base of 100 MVA and 220 kV will be given to you if so. In this textbook, it is not given because it is referred in line with that. Hence, it is being written in the solution part. So 100 MVA base, 220 kV as a base voltage. Then this megawatt transfer 500 divided by 100 terms as 5 pu. Then power factor of 0.85 and angle is inverse cos 0.85 as 31.79 degree. Then active power being 500 megawatt. What is the reactive power? Vi sin phi will get as 309.87 or 3.09 pu divided by 100 again. Then base impedance. So somebody was asking me why you are require base impedance, because here in this equation Rp and Xq, R and X I want to calculate. The transmission line possessing resistance reactance per unit length into length, if I multiply I'll get it. They are in ohms. How to get per unit length of that? Hence I require base impedance. Base kV square divided by base MVA. 220 square divided by 100. 484 ohm is the base. Then resistance I calculate. Resistance per kilometer is 0.031 into length of the kilometer is 200. It is 0.031 into 200, 6.2 ohm. This divided by 484 give me per unit ohms. Means ohms to per unit representation. Similarly, X 0.32 into 200. You can see 0.32 200 divided by 484 give me 0.1322 pu. And voltage is 220, nothing but 1 pu. Using this exact formula, E square equal to V plus Rp by V plus Xq by V whole square plus Xp by V minus Rq by V whole square. No need to remember this. This has to be spontaneously obtained by drawing the vector diagram, which just I have revised. Just draw that, just you have to connect this, or if you remember, fine. All the values just use substitute in per unit. Wherever there is a V is default 1. 1 pu, 1 pu, 1 pu. You can see. So R and P, all the values are in per unit representation. So this is a very simple substitution problem. Once I solve this, I'll be getting voltage as 1.6 pu. Suppose in this equation, exact and approximate, R is neglected. R is neglected here, R is neglected here. What happens? You can just see. R term is eliminated here. This is called approximate. Means resistance is neglected first time. Once I approximate, the terms become simpler. Then I'll be getting 1.557 pu instead of 1.6. Then the error is from 1.6 is gone down to 1.557. Error is 2.6%. Even if I neglect resistance, there is an observation of 2.6% error. If I go completely an approximation where all these values are taken out, you can just see Xq by V plus V. So this is totally taken off. Then square is also gone out. This becomes 1.4096. This way it is 11% error. This way we have exact method, resistance neglected, and completely approximate method. This is the value. So this is asked actually. You can see accurate and approximate formulae. So we need to look forward. If the sending end voltage is E is specified, then we can see sending end voltage, receiving end, sending end voltage E is specified, then receiving end voltage V is this way, if R equal to 0. So this is how one application we can just get into. Then this is another problem which is similar way. Just you can see here a 3-phase 11 kV bus drawing a certain complex power connected. Then we have data given. Find the sending end current, receiving end current, regulation, all these short circuit capacity of the system. Using similar concept, you can just outline. I'll not be just working upon this. Just look into this problem. All the equations which have been referred, the same equation have been put in line. I have just made in one page only, so that at least you can glance it clearly. So this is how a knowledge of transmission line, knowledge of complex power, active and reactive power per unit calculation have to help you. This way you can need and reach. then this is the problem of your type in the examination. Let's see a very simple problem. Consider a transmission mechanism. This is called a radial system actually. All the values are mentioned are per unit as a reactances. Respective bases on a base of 100 MVA determine power supplied by the generator and its power factor. So what is the meaning of this one? You have a generation setup here, you have a load here, you have a load here. You have 5 buses A, B, C, D, E at different voltage. A is working at 220 kV up to B 220 kV. C is having a transformer here. Okay, it is shifted by 132, means there is a change here, 132 kV. This 132 kV up to D, and later E is 11 kV. You can just see 220, 220, 132, 132, 11 kV. So load at the extreme right is at 11 kV. Load at the bus C is at 132 kV. However is that given, you will not worry. All the reactances, transmission line, double circuit, transmission line reactance are given, transformer reactance are given, loads are mentioned, and base value is 100 given. Now my ultimate task is, because of this load at the E bus number E, load at the bus number C, active and reactive depending upon the type of the power factor, what is that total power that has to be delivered by this synchronous generator? There is a P demand, P demand. There is a Q demand because of power factor lagging. There is no Q demand because of UPF. But system is inductive. System is inductive, it absorbs inductive. So there is a reactive power absorption by the transmission system and the loads. What is the total active power delivered by the generator? What is the total reactive power delivered by the generator? Reactive. I have to calculate. Once I know P and Q, getting its power factors, inverse tan ratio of Q by P. That I will do. That is the task given. This kind of question paper, exam question paper problems you will find. For this, my friends, just observe the steps. You have to go reverse. From the E, go reverse to the A. See here, from E, I move backward. So C to E, I just stop. C to E, because there is a load here, there is a next load at C. From this load, where is the next load? Till that point I should go. Bus C is having a load between C and E. What are all the points I have? There is a transmission line reactance 0.15 parallel with 0.15. Transformer with the 0.1 pu, 0.1 pu in parallel. So what is the total reactance between these buses? I have to calculate. Let's call as reactance from C to E is 0.15, 0.15 parallel. Am I right? 0.1, 0.1 parallel. If I work it out, 0.1 into 0.1 divided by 0.1 plus 0.1, 0.15 into 0.15 divided by 0.15 plus 0.15. Add them. That's what I do by simple parallel configuration. The same thing is being done here. 0.15 plus 0.1, same number is there, divided by 2. That becomes net reactance between C to E as 0.15 pu. Then reactance between A to C. C is because there is a load. C to A. Again I have 0.1 pu, 0.1 pu parallel, 0.04, 0.04 parallel. You can see here 0.1 plus 0.04 parallel divided by 2. That is a net reactance. So I get A to C as 0.07. Why I am calculating this? You might wonder. It's because there is a reactive power absorption at this bus because power factor is 0.8. Here there is no power factor lagging. It's a UPF, only active power transfer. But to transfer this active power, inductive path is involved. This path absorbs reactive power in meeting active power. To calculate that, I obtain reactive power, reactances of that line. But here reactive power by the load, by the line happens. To compute that, I require this. This is the conventional step-by-step procedure. Next, I move next one. At the receiving end, what is that? Receiving end E. Load is 100 megawatt. Power factor is 1. No reactive power. 100 divided by 100. Stand as 1 pu. You can see here. Stand as 1 pu. Q is 0. Then what is the current possible there? I square. You have to remember this equation. I square equal to P square. What is being drawn? plus Q square, what is being drawn, divided by at what voltage? V square. So P square plus Q square divided by V square stand as I square. So whatever the voltage square is 1 square only. P square means what you computed in per unit. Q square means what you computed in reactive power per unit. So it is 1 square plus 0 plus 1 square as 1 pu. Current square is 1 pu. You might ask me why you compute this current here. Because to deliver this power has to flow from this line, correct? C to E reactance I got as 0.125. I square X if I do, total reactance into I square. Is it not the reactive power drop here? Yes, that's what I want to do here. I square I calculate 1 pu. Reactive power loss from section C to E is I square X. 1 square into 0.15. So to deliver 100 megawatt active power or 1 pu active power, transmission setup absorb I square into X, that is 0.125 pu reactive power. This is the absorption of reactive power, has to be compensated by the generator in this case. That have to calculate. Then at bus C, this is load loss I calculated. At this bus, I have one more load here. What is the load here? 100. 100 divided by 100 is 1 pu. Because of 0.8 power factor, I have to calculate reactive power also. That's being done here. At bus C, we add the load to the loss, which is called as, we can see here, P is, the load is 1 pu, 100 and 0.75 pu. How I got this 0.75? This 0.8 pf lag. This is active power. What is the reactive power? Get this angle. Inverse cos 0.8. Tan phi into 100. Tan phi into 100. Phi is cos inverse 0.8. That give you this value of 75. 75 divided by 100 is 0.75. My friends, look here. This is actually 100 and it is 75. When I convert per unit, divide by 100, divided by 100, it became 1. This became 0.75. This is the actual load at bus C. I come back. Load at bus C. To deal this, generator has to pump power from the left hand side. As well, power has to flow here for a forward load here. What is that net power at this bus C? Is power required by this, power required for the forward load. I have to add here. That's what you can see. Total power situation at C is, for this load 1 pu, exactly 1 pu. For the previous bus load E, 1 pu. 1 plus 1 is 2 pu active power. What is the reactive power of the bus load C? 0.75. What was the reactive power of the path of the C to E? Here, there is no reactive power, but the reactive power is absorbed by this section C to E. That's called I square X. You can see here 0.125. So, reactive power at bus C is actual load reactive power at bus C 0.75 plus forward moving power 0.125. That is net Q at bus C 0.875. This is the scenario up to bus C. From C, I have to go backward up to A because I have to go to the generator. This is another section. There is an I square X drop here also. Yes, we know that 0.07. If I know the current here, I square into current is reactive power drop. That reactive power drop and the reactive power absorbed, active power flow, active power loss, I can calculate. That you can see here. Loss in section AC. AC means generator bus to C is I square X. This is I square. What is I square? P square plus Q square divided by V square. What is this P? 1 plus 1, 2 square. What is Q? Net Q flowing out of bus C, 0.875 square, divided by 1 square. Whatever the voltage, it is 1 square because of the base. Into path reactance. What is the reactance of the path between A to C? It is 0.07. That is what is 0.33 pu. There is an absorption or loss of 0.33 pu. Because of this, this reactive power will get raised. How is that? 0.875, which is flowing from C towards E. As well at C, A to C drop is 0.33. Add this to this. That become total reactive power Dispensing from A bus is 0.875 for all plus the drop between AC. This is 1.208 pu. Then generator is now loaded with active power of 2 pu, reactive power of 1.20. Then using this, what is that? Tan inverse of 1.208 divided by 2. If I take, this is the angle, cos of that is power factor. Very simple problem. So like these problems are sure to come in the exam. Last time this kind of problem has not come. Please note this step: a transformer, a transmission line reactance, load 1, load 2, generator, different voltages. They will not harm you. What you have to work is, where is the load, convert it to pu. From that point to the next step load, get the drop in the reactance. Then at that load point, total outward flow. From that point to the next point or generator bus, drop in the reactive power. Account the total power and summarize the load of the generator. That's all. So this way, this problem need to be worked out. Take care. This is one of the solved problem I have taken. Like this problem, you may get in your internal assessment test also. Okay. So take care. Such problems I have shared in 7th sem as well. So this is how we can do. This is another variant, a T-like section. So this kind of problem has come exactly in the last exam. Maybe the same problem, I feel so. So 3 generator stations are connected by transmission lines X, A, C at point. A 275 kV line, 132 kV line, and 275 kV line, etc. For a particular system load, the line voltage at bus bar falls by 2 kV. Calculate the required reactive power injection required to bring back the voltage to original value. All pu values are on the base of 500 MVA. It means A, C, X are connected by transformer and transmission line. Suddenly, due to a system load at X, voltage falls by 2 kV. How to correct that drop of 2 kV by a compensating device? Or what is that reactive power if I feed? This drop of 2 kV is nullified and voltage is maintained back. That's the requirement. Then to do work with this, system is having ohms values of transformer and transmission line respectively in pu and ohms. Convert them into pu. Let's see. The base of impedance, this is 132, 275 a transformer, and this line is connected to 132. Assume that this must be 132, 275, 132. This line is going straight like this. Means voltage here is 132, means transformer's second side is 132. And this is connected to another transformer, shifting it to 275. Now I will say J50 ohm, J50 ohm, J50 ohm. All these are working at what voltage? 132 kV only. Then it becomes necessary for me to convert it into per unit value. Then what I should do? What is the base voltage of this? Because the 132 kV working, 132 kV is taken as a base, kV square divided by MVA. That give me base impedance. You can see here, 132 square divided by 500 MVA base, give me 34.484 ohm as a base. Now it becomes easy. 50 divided by 34.84. If I calculate, that become pu. All the values become per unit immediately. So therefore, you can just see. You have been given 1 point. You can see here. ZL is 50 divided by 34.44, become 1.4348. Now we can go back and see this reactance in series with this. This is only straightforward. This reactance is series 0.1. One element with the 0.1 pu, another with the 0.1. Only one is left off. Just you can see. So one is with the 0.1, another with the 0.1. Remaining is directly. So between bus and ground. So connect as synchronous generator to get your requirement. Single phase equivalent circuits of the figure like this way. From X to N, what is the total reactance in equivalent? So I find all the three in parallel, correct? How to get equivalent reactance of this? So we have to calculate. That's being done. 1 by x equivalent is 1 by x1, 1 by x2, 1 by x3. X equivalent stand as 0.5 pu. Then what is that short circuit current possible? E by x equivalent. So 1 pu if I apply here, 1 pu if I apply here, 1 divided by net reactance is nothing but short circuit current what would flow. That's what I am doing. E by x, 2 pu. Then base current, like your base impedance, how I got here. Base impedance, how I got here. Base current, I want to calculate. Base current is the power 500 megawatt divided by root 3 voltage. That becomes base current. So this pu and this, if I multiply, I'll be getting current in ampere. 2 pu, I have to convert to actual current. 2 pu into base current. If I multiply, 4,373 ampere I'm getting. So when 3-phase Q is required and V is the line to line voltage, then we have dou Q by dou V, sensitivity of reactive power on voltage. Then it is called root 3 ISC. Root 3 into ISC if I operate 4373 into root 3. That give you 7574.2 var per volt. Then if I make it kilowatt, it will become 7.57 MVAR per kV. So required reactive power for a certain drop of voltage, it is 7.5 MVAR per kV you need to apply. For 2 kV, how much? 2 kV is a drop. Into 2 kV, if I multiply, I have to interconnect 15.14 MVAR compensation to account 2 kV drop. Therefore, this is a synchronous condenser based approach or reactive power compensation at the point of requirement, optimal point of requirement. By what reactive power? If I connect MVAR per kV, I get it from short circuit current. From this short circuit current, root 3 into ISC give me dou Q by dou V. This value give me required reactive power per kV if I convert it to MVAR per kV. Then what is the drop in voltage? Multiply it here. 7.59 into 2. So it is 15.14 MVAR. If you install at X, the value of voltage which is dropped by 2 won't be experienced. There is a normal voltage what it was earlier. This way